and today we'll present our project on home credit default risk. We focus on this topic because individuals with insufficient credit history often struggle to access financial services under traditional credit evaluation. So, to address this, we aim to develop a predictive model that helps financial institutions better assess default risk. We have two target variables. One is high risk, means that applicants likely to default. The other is low risk, means that they have less likely to default. Then we start our data exploration to understand the overall picture. We find that most people are female, married, lack fixed assets like cars, and they have only the secondary education. This highlights that the group faces challenge in accessing credit. And then we look at the target variable. We observe that there is a clear imbalance. For example, like 92% are low risk, while only 8% are high risk. This imbalance poses a challenge as model can overlook high risk cases. And for more details, we analyze in our notebook. Then, to prepare the data, we follow a structured pre-processing strategy. First is data missing. We find that there are some features that have more than 40% missing values, so we directly drop them. While for the remaining missing values, we filled them with the min or the mode. Then we calculate our outlier and log transformations to make sure our numerical features less skewed and closer to the normal distribution. And then we do the typical standardizing and encoding. And since we have more than 100 features, we address multicollinearity by removing features with a VIF bigger than 10, means that those features were large likely explained by the others. And finally, we need to tackle our target imbalance. We applied Smolten, which generates samples for the high-risk classes, so the overall models could recognize the patterns in both high-risk and low-risk applicants. And then I hand it over to my teammate Hebe Chen to explain our model.
We computed 8 models in total. First of all, we had a logistic regression without regularization as our baseline model. And later on, we also have LR with regularization and bagging of LR. And we also computed decision tree models and random forest tree models as our tree models. And further on, we explored XG Boost and LightGBM as variation of tree models. We also computed KNN as another variation. On the main modeling method we use is grid search CV with cross-validation equals to 5. And for random forest, we computed random search with OOB arrow because random forest requires a lot of computational time. And now I'm going to specifically talking about why we chose to further explore XG Boost and LightGBM. We explored these two models as they improve upon traditional gradient boosting methods with significant optimizations. For XG Boost, it is faster due to parallelized tree construction, which processes multiple features simultaneously, and it also provides regularization to control overfitting and tree pruning to simplify model. And for LightGBM, it reduces computation using a histogram-based algorithm. Continuous features are built into intervals, speeding up the split searches. It also grows trees leaf-wise, unlike XG Boost's level-wise growth, focusing on areas with the highest arrows. This improves performance on imbalanced datasets. These two models offer numerous hyperparameters for fine-tuning, providing flexibility to control their behavior. And they also have contradictory tree growing strategies, so we choose to test both of them to compare their performance. And here is the model comparison for all 8 models based on 3 metrics. Overall, the LightGBM has the highest cross-validation scores. So later on, I will let Alia Lu to further explain on the results.
We achieved promising results on the task set using the LightGBM model mentioned above, and then to derive actionable insights, we use gating importance from it to measure each feature's contribution to the loss reduction. The raw scores were normalized into percentages for clarity, and the results are as follows. We then grouped the important features into 4 dimensions, with urgency of financial needs being the most critical, accounting for 35% of total importance. High-risk applicants check their credit records more frequently and submit applications earlier, reflecting greater financial urgency. The economic level dimension contributes 15%, with high-risk applicants showing slightly lower total income, highlighting the role of financial stability in risk assessment. Credit history and completeness of application documents provide further insights. High-risk applicants have lower external credit scores, indicating weaker credit histories. Document completeness, such as providing phone numbers or key files, improves the model ability to assess applicant reliability. In summary, frequent credit inquiries and early applications signal financial urgency, while lower income and credit scores highlight economic and credit risks. Focusing on the top features, number of credit bureau inquiries, and hour of last application submission, alongside external credit data and document completeness, can optimize risk evaluation and reduce uncertainty. In the next phase of this project, we are aiming to take things to the next level. First up, we'll experiment with neural networks to push the boundaries of what our model can handle. Then, we will supercharge the tuning process by swapping our traditional methods for Bayesian optimization, a faster and smarter way to find the perfect model settings. These steps will help us build a stronger, smarter, and more efficient solution.